Okay, let's start. So good morning, everyone. Today I'm very glad to give a lecture about learning to rank for machine learning ranking for web and vertical search. So my name is Chang from Yahoo Labs in Sunnyvale office. So here is the outline of this talk. First, I will introduce what is MLR, machine learning ranking. In the second part, I will give an overview about Yahoo Learning to Rank Challenge, which has happened in 2010. In the third part, I will introduce machine learning ranking for dynamic web content. Because as we know that web content changes very fast, how to return the most recent result, most fresh result is a very challenging problem. So we have several research papers about this topic. The fourth one is about machine learning ranking for vertical search. Because web searching is important, but different verticals, something like news, something like local search, something like shopping search are also very important. How to handle this kind of vertical search is a slightly different problem, and we did some research about it. Okay, the first part I will introduce what is machine learning ranking, we call it MLR. Before that, first let me spend a couple of minutes to talk about the history of commercial web search engine. The first generation of search engine we call syntactic matching, starting from 1994 to 1997. The representative including Excite, Lotus.com. So the characteristic of the first generation search engine, they only use the on-page information. For example, they are using the text matching information. Given a query, we need to match the content on the web page. Also use some traditional IR information, something like TF-IDF. I think some of you already learned about it yesterday, etc. So most of them only use the on-page information. At the beginning, it is very convenient, very useful. However, later, different other companies, other search companies use more rich information to improve the relevance of the search engine. The second generation of search engine, we call use some off-page information, some web-specific data. For example, starting from Google in 1998, they are using some of their web link information. At the beginning, it just started from Google, but later it is widely used by almost all survival search engine companies. Link analysis or link structure is first proposed by PageRank. If some of you use a search engine 10 years or 12 years ago, many of us at that time was really impressed by the quality of Google. And when we are trying to figure out why Google can return very good result, Google claim, PageRank. So at that time, people have some curious, we have some question, why Google's quality is so good? PageRank, just because PageRank, or they have some other secret. So at the beginning, many people just believe Google is smart because of PageRank. But later, we realized PageRank is more like just a trademark for Google, because the concept, the idea of PageRank nowadays is widely used by every search engine company, like Bing, like Yandex, like Baidu, etc. Also, the second generation using the click-through data, because before using click-through data, different companies, search engine companies, either use some human expert creating some rules, but this kind of rules sometimes is not scalable, or use some editorial labeled data, but which is very expensive. Click information provide us almost infinite amount of data, but it is very noisy. So how to properly use the click information is a big challenge for search engine. Also use anchor text. Anchor text is also very important because anchor text is more like an extension of the web content. And anchor text is something like crowdsourcing, because different web page will link to a web page and show their explanation, show their own understanding. So anchor text sometimes is even more important than on-page information. The third generation of search engine is one step further than the second generation. The characteristic of the third generation, one is use the semantic analysis and trying to answer the need behind the query. And the third generation of search engine is still evolving. Now, there is only a few search engine player survives, like Google, Yahoo, Bing, Yandex, mainly in Russia, Baidu, mainly in China. Yeah, that is only a few survival search engines. And the third generation of search engines, they are focused on user need rather only on query itself. So it's one step further. So not only find something related, but also first to understand what is the user's need, what is query intention. And another characteristic for the third generation search engine is trying to integrate multiple sources of data. For example, it is so-called universal search quite a few years ago. For example, nowadays, most of search engine, when you search a query, it will return some of the images, video, UGC, for example, like the social content, together with the web search data, which is help user to find what they need just with one query instead of go to different place to find different separate result. And another thing is the third generation is trying to facilitate users. For example, like a spelling correction, like a query suggestion. For myself, I'm not a native English speaker. So sometimes when I type in some queries, I have difficulty about spelling. So spelling correction can help many international users to type in a query very efficiently and effectively. When it comes to the mobile, it will become more important. When we are using the PC, sometimes we can type in a query very quickly and very efficiently. However, when it comes to the mobile, how to type in different characters is very difficult. So ideal case, whenever I just type in one or two, a couple of characters, and it will automatically recommend what is the true query I may want to input. So that is what we call the third generation of search engine. Okay, what is machine learning ranking? We call it MLR. So a few years ago, I read an article that said machine learning ranking is the largest AI or machine learning application in the world at that time. I'm not sure whether it is still the largest one now, but I'm pretty sure that a few years ago, it is the largest machine learning application at that time. Why? Because for some big search engine company like Yahoo and Microsoft at that time, each company will hire 100 or even a couple thousand of editors just to label the training data for the task. So this kind of editors, they work every day and trying to get more labeled data as a training data for the machine learning ranking problems. Okay, so for machine learning ranking, because it is a machine learning task, right? For every data point, actually that is a query URL pair. So a query and a URL pair converted into a feature vector as one data point. And the learning target is the human labels. In different companies may have different variations. For Yahoo, we ask editors to provide 5 grade different labels, P, E, G, F, B. P means perfect, E means excellent, G means good, F means fail, B means bad. I'll give an example. Think about if you search a query, Yahoo. If a search engine return yahoo.com, we believe it is a perfect match because this query is more like a navigational query, and the yahoo.com is a navigational result, so that is perfect. If a user, for example, in Indian, search for Yahoo, ideally, yahoo.com, Yahoo Indian should be the perfect match. But if the search engine just return yahoo.com, it is not Indian result, right? So it is still good, but definitely not perfect. So we label it as excellent. If a Yahoo, if a user search Yahoo and the return result is about, for example, Yahoo News or Yahoo Finance, the result is relevant but not that good. So we mean it is good. If return a result about some news about Yahoo and some news together with maybe some rumors or relationship, we ask editor to label as fail. So it is somewhat related to Yahoo, but not that related, given the query just Yahoo. And if just search Yahoo and return a spam page or LDOT page or whatever page, we call it as bad, which is totally irrelevant. We're trying to avoid this bad result because bad result will really hurt the user experience of the search engine users. So for machine learning ranking, offline to do the training and online to do the testing. And the evaluation use a matrix called the DCG. The basic idea of the DCG is it can both consider the human labels by the G and also consider the position that is controlled by I. The basic idea is we want to return the high quality result to the user and return the best high quality result on the top position. So ideally, we need to put the perfect result at the first position, excellent result on second position, etc. And it could have multiple excellent result, multiple good result, etc. Okay, so in terms of the ranking permission, first, when we are reading some textbook, for typical machine learning task or data mining task, including like classification, including regression, including clustering, recently including something like causality. But I believe ranking is also a fundamental problem for machine learning because it provides not only the score, but provide this kind of ranking result. And ranking not only used by web search or vertical search, it have many other applications on different machine learning tasks. Today, when we're talking about the ranking, I'm more focused on the web-related ranking. So for the mission is to satisfy all users by providing the best algorithm result to your query. So ranking is about, first is to understand a query and about its intent. For example, given a query, and we know that it has some shopping intent or about some news intent. So we need to figure out understand the intent of the query. And ranking is about collecting as much information as possible about the query and the potential result. And ranking is also to determine how well the result answers a query and ordering different results in the best way to optimize the relevance. So what is the benefit of machine learning ranking? So first is MLR learn by example. So there's no need for hand-tune ranking functions. In the old days, there are some of the human expert system need a lot of hand-tune efforts. If we use machine learning ranking, there's no such kind of problems. Some of you may have some questions because it was reported that Google still use some hand-tune based method. And in China, Baidu is still use some hand-tune method. But to the best of my understanding, to the best of my knowledge, in Baidu and Google, they also use the idea of machine learning ranking to generate different meta features. And finally, maybe due to some legacy issues, their final result is more or less handled by the hand-tune method. And the efforts moving from tuning to create training data is very efficient. For example, if we have a good ranking result, like for US market, then we can quickly train another ranking function, for example, for some new market, like in Arabic countries. And machine learning ranking can also use diverse information because it is a machine learning task. So we have more than 1,000 different features. And a machine learning model which can easily incorporate new features and which is very flexible and effective. And machine learning ranking also leverage mature and effective statistical learning techniques. And some current ranking, for example, using the gradient boosting, using something like random forest, etc. And machine learning ranking also is very efficient and very easy for experiment. So we use parallel, we use grid computing. We can do hundreds or thousands of examples together in a batch mode. And there's another benefit is machine learning ranking significantly improves the relevance for real commercial search engines. Okay, so next slide, I will talk about the components of MLR. So first, I will talk about the training data, how to collect training data. The second part, I will talk about how to generate effective ranking features. In the third part, I will talk about the ranking algorithms. So ranking algorithms, as I mentioned, not only benefit for web search or vertical search, but also can apply to many other machine learning tasks. And the fourth one is about evaluation metrics. Okay, for training data, so first is, as I mentioned before, so all page are editorial judged into 5 grades: perfect, excellent, good, fair, and bad. And we also did, we also try to collect many different sources of training data to minimize the bias. For example, at the beginning, we just random sampled some of the queries from a search engine, and we hope that this type of queries can unbiasedly represent the true distribution of the queries. But later, we also did some other data collection method to trying to enrich the training data. For example, experiment PI, that is, we random sample the query based on the distribution of the true input queries. And we also did some competitive tests. For example, compare Yahoo search result with Google, with Microsoft, and get the top result also from our competitors. For example, if one search engine like Yahoo at some time, given a query, all the search results are bad, but if we can find some good result from Google, then we can include that into our training data, which means to balance the training data, have more good result. And we also have some, active learning PI. Active learning is very important for machine learning tasks because active learning can most effectively collect some of their training examples. Sometimes, for example, near the decision boundary. Sometimes some of their queries, some problems are very difficult, and we can use active learning. Yes?
So while preparing the training data, how do you take the time into account? For example, for certain queries, certain result is good or bad often depends on what time the query has been made. For example, if I search for Roger Federer right now, news about him losing last night.
Yes.
Much more.
It's a very excellent question. Actually, it will be covered on the third part of this presentation. So machine learning ranking with dynamic web content is all about this content. So I'm currently talking about the first task. That is just some introduction. So for specific questions, something like record freshness or recency, I will introduce it later. Okay, some active learning, which is also important, and some of their click PI. For example, we find some queries, have a lot of clicks about some of their result, and which means a lot of users like to click some of the URLs. Why the user like to click it? So we can ask editors to label this kind of result. And finally, we also, for some of their query, especially some very difficult queries, sometimes all search engines fail to find a good result. In this case, we would ask editors to create the result and put it into the training data. Okay, that is the training data collection for web search. So later today, I will talk about how to effectively collect the training data for different applications, something like a vertical search. Okay, the next part is about the ranking features. So ranking feature is very, very important. Generally speaking, we can categorize feature types into 4 different types. The first one is we call document-dependent queries. Actually, it is only document-dependent queries. For example, web graph, page rank. The basic idea is if we consider different web page just as a node in the web, and consider their in-link, out-link as an edge between the nodes, then we can do some, we can run the page rank or random walk algorithms to figure out the relative importance of each page or each website. So as I listed here, as we know that page rank just one feature among thousands of features. So page rank is important, but page rank is not everything. Page rank is just one important features. And some other important features, something like document statistics. For example, how long is a document, and what is in-link, outlink of this in-link, outlink of this document, etc. So this kind of information provide us some weak signals about each document. So which signals means if we only consider this type of feature, maybe it is not that informative. But if we have a lot of training data, and the document statistics have some correlation, some are positive, some are negative, with learning target, it will provide some information for our machine learning tasks. So some BB, I don't know. Do you hear some noise about it? Okay, anyway. So another part feature is document classifier, which is also very important. As we know, some of the document is about news document, some of them is about some spam document, some may be labeled as elder documents. So this kind of information can help a search engine to make good prediction what the query it is. The second big type of query is we call query-dependent feature, which is only dependent on query. For example, the intent of a query, whether a query is about news intent, whether it's about shopping, it's about local, and what is the statistics or some of the attributes, some of the characteristics of a query. For example, like what is the language of a query. Similarly, if we just know the language of query, maybe it's less important. But if we also know the characteristic of a document, for example, if a query is in Japanese, and we know that a document is also in Japanese, that is a good match. And another page is a page in Chinese or in Vietnamese, that is a bad matching. So document attribute and the query attribute combined together would be more important than just use them alone. The third category is we call query document dependent features, which means some of their features are related to both query and document. For example, something like the text matching features, including the most famous one is called BM25, which is a very famous feature in information retrieval. There's some other feature we call the topical matching, which means we know that this query is about, for example, about news intent. And this document is news. So this kind of matching is important. Among these three, query document dependent features, the third one is the most important. However, there are some difference among these features. For example, document dependent features, they can be pre-computed, which means they can be computed offline. And so we can generate some of very complex features, something like page rank. Maybe some of you tried the page rank before. It would become a huge metrics and run the random walk or PageRank algorithm, it will take a long time. But if we can compute it offline, we can compute it in advance. So we can generate some very computational expensive features in advance. For query-dependent features, definitely, if a query is inputted right now, we need to generate this kind of features in real time. So which means query-dependent features should be very fast. The same thing, query document-dependent features, because it is related to query and document in real time. So we need to generate this type of feature very quickly, very efficiently. Sometimes if some of their research features, on some research papers, show some very promising signals in terms of query-document correlation, but sometimes due to the computational cost, we cannot leverage into a real search engine. By the way, so maybe when you try a search engine, if you try a search engine like in Bing, in Yahoo, in Google, you find all the search results are returned in 0.01 second, or for example, 100 milliseconds, etc. So we have some experiment in the past. So we find that users, especially the user search engines, they are really, really picky. If compare different search engine, if one search engine is 200 milliseconds slower than the other search engine, a lot of users will avoid using it. So which means when we are trying to compute this kind of features, we need to generate features very quickly, very efficiently with a lot of grid computing power. But no matter what, those kind of features cannot be too complicated. I mean the query feature and the query document features. And there are other features we call the other features because it's difficult to categorize them within one character. For example, click feature. Click feature is very important. And there are many different, we can derive many different click features based on users' click information. Another one is we call the external reference features. For example, maybe some of you use Delicious. Delicious sometimes can provide good signals for some of their queries. And also, there are some feature about Twitter. So I will introduce some of the Twitter-related feature in later of this talk. And there are big family of features which is time-sensitive, which is some of the feature is very time-sensitive in terms of time. So as you mentioned, that how to handle this kind of feature to provide the best result for those kind of time-sensitive queries is also very important. So yeah, let me talk more about the document feature. For example, spam, whether a document is spam or not. What is the quality of a document? And whether a document is held out or not. And there are some other page category features, something like whether a page is a blog page, whether it's a 404, which is cannot be, is no longer survived page, whether a page is about a download page, it's just full of download links. And what is popularity, what is the trust of a page. So this idea, as you can imagine, is a little bit similar to PageRank, but sometimes we leverage many different variations of PageRank, and sometimes we leverage different kind of, PageRank is mainly handled by popularity, but sometimes we have some other information about the trust based on the domain knowledge or based on some of their other signals, something like based on tweet information, we can derive the trust signals. And another is about the language, about the region. Language, easy to understand whether a document is in English, in French, in Japanese, in Chinese. Region is about what is the page is in which region. For example, whether the website is in United States, or in Vietnam, or in China, or in India, etc. Query features are something like a query length. So, yes?
The quality of a page. So how do you quantify the quality of a page?
Okay, there are many different variations of the quality. Sometimes for a commercial search engine, we're just trying to leverage different variation of quality. Some quality, for example, what is the average page view of this website? Because we believe, and for example, what is the duration of a web page? Because sometimes we go to our website because we intentionally go to that website, so the duration time will be long. But in some of the cases, some of their page is just something like spam page. They just, no matter what, I was redirect to that page, but it's just a spam page, so I quickly left it. So this kind of signals can provide us some signals about the quality of a page. And this is just one example. There are many different aspects to measure the quality of a page or quality of a website. Okay, query features, for example, the length of a query. Generally speaking, the longer the query, the more difficult. Especially, there are some query which is natural language query, especially when we use mobile. For example, what is the distance from Bangalore to Mumbai? So for some of the natural language queries, maybe for some of them, maybe we cannot find the exact match online. How to handle those kind of natural language and trying to convert a natural language query into an effective query is something, another challenging problem. And what is the frequency of a query? Something like how often people search such a query, etc. And the frequency of each turn and the average host entropy of a query's search result. Query category, for example, whether query is a navigational query, LDOT, commercial query, etc. By the way, navigational query or navigational page is repeatedly in these slides or repeatedly in